So now let's do a generic UV transformation. Here is our integral. The region which we are integrating over is going to be some trapezoidal region. Now that trapezoidal region connects the points 0, 1, 0, 2, 2, 0, and 1, 0. And you can see this trapezoid, which I've shaded in yellow, which is clearly not a polar region. Anyway, the goal here is to seek some function. X is some function of u and v, and y is some function of u and v. That's the ultimate goal. And if we have those functions, then we can simply plug those functions in for x and y respectively, calculate the Jacobian, and then evaluate the integral. So we seek x is some function of u and v, and y is some function of u and v. And this is going to be like the u substitution problem that we worked in single variable calculus. To do this, we need a strategy similar again to the u substitution. This time, though, we would like a u and v substitution. Now, this is somewhat arbitrary, your choice in u and v, and that gives some feeling of why an absolute value sort of standardizes this. But anyway, you could probably guess, if you were making a guess, what u would be as y minus x, and then the v consequence would be y plus x. And keeping in mind that the thing that we seek are these functions, then I just need to manipulate this a little bit to get functions of x and y in terms of u and v. You notice here that if you add the two equations, then you get u plus v equals 2y. And if you subtract the two, I'll do it in this order, v minus u equals positive 2x, then we get the thing that we sought. Y now is going to be 1/2 u plus v, and x is going to be 1/2 v minus u. That gives us what we want. X is a function of u and v. Y is a function of u and v. Let's write out our transformation. X equals 1/2 v minus u. Y equals 1/2 u plus v. Next step, let's do the Jacobian. The Jacobian is the partial derivative xy over partial u v, and that's going to be par x, par u. Get used to the rhythm of this. We do x's across, par x, par v, and then we do y's on the bottom. Par y, par u, par y, par v. Let's find those particular values. The partial derivative of x with respect to u is simply negative 1/2. Partial derivative of x with respect to v is positive 1/2. And then along the bottom, 1/2, and the partial derivative of y with respect to v is also 1/2. Good. Remember, this is the determinant bars, and so this is going to be negative 1/4 minus 1/4, which comes out to be negative 1/2, and then the absolute value of the Jacobian comes out to be 1/2. Let's write the resultant transformed double integral. For now, I'm just going to say we're going to do that over region T, the transformed region, and so this is going to be e to the power of u over v times the absolute value of 1/2, and then I'll just say du, dv, and those can be switched later if needed. So we pull out the 1/2, double integral over the transformed region, e to the u over v du dv. Now, one of the really tricky parts here are the bounds of integration. Let's draw our attention back to the trapezoid, which was made up from these ordered pairs, but we actually have these line segments here. So this line here would be x plus y equals 1, and then the line over here would be x plus y equals 2. And of course, we also have these equations here. This one is y equals 0, and this bound over here to the left, that's going to be x equals 0. All right, here we go. For the bound x plus y equals 1, if we use the transformation that we did above and wrote x as 1/2 v minus u plus, and then the y 1/2 u plus v, and that equals 1, then that, if you simplify it, is going to come out to be v equals 1. Let's take a look at the next bound. X plus y equals 2. In a similar fashion, 1/2 v minus u plus 1/2 u plus v, that equals 2. And if you do the simplification there, it comes out to be that v equals 2. Now let's take a look at y equals 0 bound and actually do that substitution. 0 equals 1/2 u plus v, and if we do that, it comes out that u equals negative v. Let's do the last one. X equals 0 bound, so 0 equals 1/2 v minus u, and of course that tells us that u equals v. Let's take a look at this on the uv plane, and your choice of u and v are arbitrary. All right, so we have v equals 1, so let's make that 1 and 2. So we have v equals 1. Now we need v equals 2. Okay. Now we need u equals negative v. And u equals v, kind of like a y equals x. Okay, hopefully you can see then that we've created a new bounded region. Also a trapezoid, mind you. I'd like to highlight that with a nice border. Okay, and now you see that we have a type 2 region in terms of u and v, and we are ready to set up and then evaluate this integral. So we had 1/2. Now we have to do our bounds, and our bounds are going to go fixed 1 to 2 in the v, and then the u is going to go from negative v to positive v. We had e to the u over v, and now our order of integration du, and the dv is on the outside because we fixed the v, and now it's time to integrate, and this is going to come out to be 1/2 the integral from 1 to 2. Now we integrate the inside with respect to u, so that's going to give us v e to the u over v, and that's going to go from negative v to v dv, which is 1/2 the integral from 1 to 2. If I plug in v for u, then I get v e to the 1 minus v e to the negative 1 dv, 1/2 the integral from 1 to 2. If I factor out a v, then I have e to the 1 minus e to the negative 1 v dv. I'll just pull that out. here we have it. Jacobian. 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 Jacobian.